January 5, 1943. Cooler Gulf, Solomon Islands. Lieutenant Red Cochran gripped the fire control director aboard the cruiser USS Helena as 4 IED-3A dive bombers completed their attack run against the American task force. These Val struck the New Zealand cruiser Achilles and were turning away with characteristic Japanese precision. Cochran armed shells containing technology that would rewrite the mathematics of aerial warfare. 2 salvos thundered from Helena's aft 5-in battery. One of the departing Japanese aircraft erupted in flames without being touched, ripped apart by shrapnel from a shell that exploded 30 ft away. The pilot never understood what killed him, neither did his commanders. Neither would the Japanese high command for the remainder of the war. This was the first combat kill by a weapon that military historians would later rank alongside radar and the atomic bomb in strategic importance. The proximity fuse, deceptively CNAM, the variable time or VT fuse, had just announced itself to the Pacific War. Over the next 2.5 years, this technology would fundamentally alter Japanese tactical calculations, shatter their aerial offensive capability, and save thousands of American lives. The transformation began not with brilliance but with a fundamental problem that had plagued anti-aircraft gunners since aircraft first became weapons of war. December 7, 1941, Pearl Harbor, Oahu. As Japanese aircraft screamed through tropical skies, American gun crews fought back with everything available. Naval guns thundered from damaged ships, hurling shells skyward at attacking dive bombers and torpedo planes. Each shell required manual fuse setting, a sailor turning a wrench against a clockwork mechanism, while enemy aircraft dove through defensive fire. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late. Some never exploded at all. Others fell back to Earth, their contact fuses still armed. In Honolulu, 9 mi from the harbor, shells weighing 55 lb crashed through roofs, detonated in streets, tore through buildings. The Hayasaki family died when a 5-in shell flew through their restaurant window during breakfast service. Father Jitsuo, sons Jackie and Robert, daughter Shirley and nephew George perished instantly along with 7 young men eating at the Cherry Blossom restaurant. 3-month-old Janet Yumiko Ott became the youngest casualty when a shell struck her home, killing her, her mother, and her aunt. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 of them had been killed in Honolulu, specifically not by Japanese bombs, but by improperly fused American anti-aircraft shells landing in the city. The tragedy illustrated with brutal clarity the inadequacy of existing technology against modern aircraft. The mathematics were unforgiving. Traditional anti-aircraft fire required 3 pieces of perfect information executed in sequence under combat conditions. First, optical rangefinders had to calculate exact distance to a target moving at 300 mm, potentially through smoke, clouds, or tropical sunlayer. Second, height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will. Third, fire control computers had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude. A sailor then manually set a clockwork time fuse. The shell was loaded, the gun fired, and the fuse mechanism counted down. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly, the shell would explode near the target. The odds of destroying an aircraft were approximately 1 in 2,500 rounds fired under ideal conditions. In combat with multiple targets maneuvering through defensive fire, the odds dropped catastrophically. The problem had existed since the First World War, but became critical as aircraft evolved. In 1918, aircraft flew at 90 mph at altitudes below 15,000 ft. By 1940, modern fighters exceeded 400 mph at altitudes above 30,000 ft. The gap between gunnery technology and aerial performance had widened into a chasm. The British discovered this reality facing German dive bombers over Dunkirk. Ships lacked space for additional guns. More ammunition consumed limited magazine space. Better fire control helped, but could not overcome the fundamental limitation of time fuses, requiring perfect prediction of an aircraft's future position. August 1940, the Department of Terrestrial Magnetism, Carnegie Institution, Washington, D.C. Dr. Merle Anthony Tuve received an impossible assignment from the National Defense Research Committee. Born in South Dakota, educated at the University of Minnesota and Johns Hopkins. Tuvit had spent his career exploring the physics of the ionosphere using radio waves. In 1925, working with Gregory Britt, he had pioneered techniques measuring the reflection of radio waves from the ionosphere to map its structure. This work laid the theoretical foundation for radar. When the committee approached him about developing a proximity fuse for artillery shells, he understood immediately that WWII might provide the solution. The British had shared preliminary research during the Tizard mission, concluding that while a proximity fuse might work in rockets or bombs, the forces involved in artillery made it impossible. A 5-inch shell experienced acceleration of 20,000 times the force of gravity when fired. No electronic device could survive such forces, certainly not the delicate vacuum tubes that formed the only available electronic components in 1940. Tuvit proposed something different. A miniature radio transmitter and receiver no larger than a pint milk bottle installed in the nose of an artillery shell. The transmitter would broadcast continuously. As the shell approached a target, radio waves would reflect back. The frequency of the reflected signal would shift due to the Doppler effect. When the frequency shift reached a predetermined level indicating proximity to the target, an electronic circuit would close, sending current to a detonator that would explode the main charge. Simple in concept, impossible in execution given the technology of 1940, the project designated Section T of the National Defense Research Committee began on August 24, 1940, with Tuvit as chairman and a handful of researchers in a laboratory at the Carnegie Institution. Their first challenge was identifying what components a working fuse required. A radio transmitter capable of operating at frequencies that would provide usable Doppler shift. A receiver sensitive enough to detect reflected signals from an aircraft several hundred feet away. An electronic amplifier to boost the received signal. A circuit to compare transmitted and received frequencies and detect Doppler shift. A power source that could provide sufficient voltage and current. A detonator triggered by the electronic circuit. Safety mechanisms to prevent premature detonation. All of this had to fit inside a space approximately 8 in long and 2 in diameter. Every component presented problems that seemed insurmountable. Vacuum tubes, the only electronic amplifying devices available in 1940, were fragile glass envelopes containing delicate filaments and electrodes. Standard radio tubes were 6 in tall and weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios and could withstand 10 G of acceleration. The fuse required tubes that could survive 20,000 grs. At 20,000 grs, a 1OZ tube would weigh $250 lb for the fraction of a second it took the shell to travel down the barrel. Forces sufficient to turn solid steel into fragments. October 1940. Laboratories across America received urgent requests from the National Defense Research Committee. Western Electric Company and Radio Corporation of America were asked to develop miniaturized vacuum tubes hardened for extreme acceleration. Sylvania developed specialized glass formulations. Rathon experimented with tube designs featuring planar electrodes that distributed forces more evenly. Engineers discovered that conventional assembly techniques produced tubes that shattered instantly under high acceleration. The solution required innovations in every aspect of tube design and manufacturing. Glass was modified with additives that increased strength while maintaining the vacuum seal necessary for tube operation. Internal components were embedded in shock-absorbing materials. Electrode structures were redesigned using spot welding techniques that created mechanical bonds capable of surviving extreme stress. By spring 1941, after thousands of design iterations, acceptable tubes emerged from production lines measuring less than an inch in height and capable of surviving 20,000 G acceleration. The power source presented equally daunting challenges. Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution. A glass tube filled with electrolyte solution sealed with metal plates at each end. When the shell was at rest, the liquid remained in the center of the tube isolated from the metal plates. When fired, centrifugal force from the shell's spin forced the electrolyte outward against small pieces of metal embedded in the tube walls. Chemical reaction between the electrolyte and metal plates generated electrical current. The battery activated only when the shell was spinning, providing a built-in safety mechanism that prevented premature detonation. May 6, 1941. Dahlgren Naval Proving Ground, Virginia. 6 prototype fuses built by the National Bureau of Standards team were loaded into air-dropped bombs and tested over water. Radio transmitters activated. Receivers detected reflections from the water's surface. Electronic circuits triggered detonators. All 6 bombs exploded at the correct altitude. The success validated the basic concept, but bombs experienced only a few hundreds of acceleration when released from aircraft. Artillery presented a challenge 2 orders of magnitude greater. By June 1941, Section T had expanded to over 100 engineers, physicists, and ordnance specialists. A former automobile dealership in Silver Spring, Maryland, became the main laboratory, with security so tight that neighbors speculated about the mysterious activities behind blackout curtains. The cover story described research into optical instruments. The reality was a crash program to develop a weapon that Allied military leaders believed could alter the course of the war. The development process revealed a cascade of engineering challenges. The antenna had to be small enough to fit in the nose while efficient enough to transmit and receive radio signals. Engineers developed a ring antenna circling the fuse body. The transmitter circuit had to generate radio frequency signals at 70 to 90 MHz. Circuit designers created transmitter designs using just 3 vacuum tubes. The receiver circuit had to detect signals 1/millionth the strength of the transmitted signal. Amplifier stages using 4 vacuum tubes provided sufficient gain. The Doppler detection circuit compared transmitted and received frequencies, closing an electrical contact when the difference indicated proximity to a target. December 1941. The attack on Pearl Harbor transformed the proximity fuse project from important research to critical priority. The Navy had been skeptical that electronics could survive gun launch. Witnessing the inadequacy of time fuses during the Pearl Harbor attack eliminated all doubts. Production contracts expanded from millions to hundreds of millions of dollars. Johns Hopkins Applied Physics Laboratory was founded on March 10, 1942, to centralize development. 5 companies received contracts to mass-produce fuses following designs developed at APL. Crossley Corporation in Cincinnati, RCA, Eastman Kodak, General Electric, and McQuay Norris committed entire factories to fuse production. Over 100 factories would ultimately participate, producing components for fuses that each contained approximately 130 miniaturized parts. The goal was 40,000 fuses per day by late 1943, 70,000 per day by war's end. The secrecy surrounding the project was absolute. Workers assembling components never knew what the final product would do. Different companies manufactured different sub-assemblies. The designation variable time fuse was chosen specifically to mislead anyone who might learn of the project. The code word PZT was used in military communications. Even after combat use began, captured fuses that failed to detonate were assumed to be some kind of advanced time fuse. Japanese and German intelligence never determined the true nature of the technology. August 12, 1942, Chesapeake Bay, Virginia. The cruiser USS Cleveland conducted the first comprehensive test of production proximity fuses against drone aircraft. 3 radio-controlled target drones were launched to simulate aerial attack. Cleveland's 5-in guns required fewer than 10 rounds to destroy all 3 aircraft on the first day of testing. Naval authorities canceled the remainder of the 2-day test schedule and immediately authorized mass production and fleet deployment. In tests over the previous 2 years, time-fused shells scored hits requiring an average of 2,500 rounds fired per aircraft destroyed. Proximity-fused shells destroyed aircraft with dramatically fewer rounds, demonstrating 25-fold improvement in effectiveness. Production accelerated through fall 1942. The first combat-ready fuses reached fleet units in October. The cruiser Helena received 500 rounds of proximity, fused 5 in ammunition, carefully distributed to prevent accidental disclosure if the ship was damaged. Instructions emphasized that proximity fuses were to be used only over water, where duds would sink beyond enemy recovery. Gunners were trained but not told how the fuses functioned. Initial fleet reaction ranged from skepticism to curiosity. The morning of January 5, 1943, resolved all doubts. Lieutenant Cochrane's salvos destroyed 1 Val dive bomber and damaged a second. The gun crews had achieved aerial kills without perfect prediction of target position, without manual fuse setting, without the complex calculations that had limited anti-aircraft effectiveness since the technology's inception. Word spread through the fleet immediately. Ships that had received proximity fuses began using them in every engagement. Cruisers, destroyers, and battleships reported kill ratios far exceeding anything achieved with time fuses. Enemy pilots noticed something had changed but could not understand why. By March 1943, 25% of all anti-aircraft ammunition issued to the Pacific Fleet contained proximity fuses. These rounds accounted for over 50% of all Japanese aircraft destroyed by naval gunfire. Proximity fuses proved 3 times more effective per round than conventional time fuses under identical conditions against fast-moving targets in night engagements. The advantage increased to 7-fold. Ships previously defended by walls of steel that relied on volume of fire could now achieve aerial kills with a fraction of the ammunition expenditure. The effectiveness of proximity fuses triggered Japanese tactical changes that Allied intelligence observed, but could not fully explain. Japanese aircraft began attacking from higher altitudes, sacrificing bombing accuracy to remain outside effective range. Torpedo bombers approached at wave-top altitude where radio reflections from the ocean surface caused premature detonations. Dive bombers released at steeper angles to minimize exposure time. These adaptations reduced Japanese strike effectiveness, while failing to restore the advantage they had enjoyed earlier in the war. American ships continued to shoot down Japanese aircraft at rates that made conventional attacks unsustainable. Admiral William Halsey credited proximity fuses with fundamentally changing the balance of power. Japanese torpedo bombers had been particularly effective in night attacks when visual tracking was difficult, and time fuses were nearly useless. With radar detection and proximity fuses, ships could engage aircraft effectively in total darkness. During 1943, despite using proximity fuses and only 25% of ammunition expended, over half of Japanese aircraft destroyed by anti-aircraft fire were killed by proximity-fused shells. October 1944, the Philippines. Japanese forces facing inevitable defeat implemented a strategy that would test American defenses to the breaking point. Special attack units officially termed Shinpu Tokubetsu Keikitai, but known universally as kamikaze, began deliberate suicide attacks against American ships. The first organized kamikaze attack struck during the Battle of Lee Gulf. The tactic was born from desperation and Japanese recognition that conventional attacks had become ineffective. Experienced pilots had been systematically destroyed over 2 years of attrition. Replacement pilots received minimal training, insufficient for bombing and torpedo attacks that required precision. Kamikaze attacks required only enough skill to keep an aircraft pointed at a target. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the nature of the threat. Conventional attacks saw aircraft approach, release weapons, and attempt to escape. Proximity fuses destroyed attackers at distances where damaged aircraft would miss their targets. Kamikaze attacks removed the escape phase. Pilots flying damaged aircraft continued toward targets, sometimes surviving long enough to crash into ships even after sustaining damage that would have caused conventional attackers to abort. The solution required concentration of fire that destroyed aircraft completely, rather than merely damaging them. Ships increased rates of fire, created denser patterns of proximity, fused shells, and engaged targets at longer ranges. The destroyer USS Hadley and destroyer escort USS Evans, operating as radar pickets, faced 156 attacking aircraft on May 11, 1945, during a 90-minute engagement. Hadley destroyed 12 aircraft before being struck by 4 kamikazes that remained airborne long enough to crash into the ship, despite being hit by anti-aircraft fire. Evans destroyed 23 aircraft before damage forced her withdrawal. Post-action analysis showed that proximity fuses had been indispensable, destroying aircraft at ranges where time fuses would have been ineffective. Without proximity fuses, both ships would certainly have been sunk in the first 30 minutes. Statistical analysis from the Pacific War documented the effectiveness precisely. Between October 1944 and August 1945, American naval forces destroyed 278 Japanese aircraft using proximity-fused ammunition. Ralph Baldwin's analysis in his authoritative study showed that only 46 would have been destroyed using conventional time fuses under identical circumstances. The 6:1 effectiveness ratio translated directly to lives saved and ships kept in action. At Okinawa, where American ships faced the most intensive kamikaze operations of the war, proximity fuses accounted for a significant percentage of Japanese aircraft destroyed, though the majority of kills still came from combat air patrols and shorter-range automatic weapons. June 12, 1944. The fields of northern France. While proximity fuses revolutionized naval warfare in the Pacific, restrictions had prevented their use over land where unexploded fuses might fall into enemy hands. German technical intelligence had proven capable of reverse engineering captured equipment, but the V-1 flying bomb campaign against London forced reconsideration. Beginning June 13, 1944, Germany launched thousands of V-1 cruise missiles at England with over 120 per day at the height of the assault. Traditional anti-aircraft defenses struggled against targets traveling at 400 mph at altitudes below 2,000. F.T. Churchill personally authorized use of proximity fuses against V-1s despite the risk of technology disclosure. Modified fuses were rushed into production at Crosley Corporation and flown across the Atlantic by special Lancaster bomber flights. British 3-7N and American 90mm anti-aircraft guns began firing proximity-fused ammunition against incoming V-1s in mid-July 1944. The effect was immediate and overwhelming. During the first week, kill rates increased from 10% to 24%. By the fourth week, 79% of V-1s were destroyed by proximity-fused anti-aircraft fire. On one day toward the end of the campaign, radar detected 104 V-1s approaching England. Proximity-fused anti-aircraft guns destroyed 68. Of the remaining 36, fighter aircraft destroyed 32. Only 4 reached London. The British capital was saved by technology developed on the other side of the Atlantic. December 16, 1944. The Ardennes Forest, Belgium. German forces launched their final major offensive in the west, attacking through terrain considered impossible for armor. The Battle of the Bulge caught American forces by surprise in weather that grounded air support. Colonel George Axelson, commander of the 406th Artillery Group at Mono, Germany, made an unauthorized decision that day. Facing masked German infantry assault, he ordered his gunners to use proximity fuses in ground combat despite strict prohibitions against land use. The emergency, he decided, trumped the restrictions. 3 days later, on December 19th, General Dwight Eisenhower formally requested authorization to use proximity fuses in ground operations. All restrictions were removed on December 21, 1944. The effect on German forces was catastrophic. Traditional artillery fired shells that buried themselves in mud or snow before exploding, directing energy downward and limiting fragment distribution. Proximity-fused shells detonated 20 to 50 ft above ground, showering fragments over areas 50 times larger than ground burst shells. German infantry advancing through open areas found themselves subjected to air bursts that no foxhole or trench could protect against. Each shell created a lethal fragment pattern, covering over 3,000 square ft compared to 60 square ft for conventional ground burst shells. General George Patton, whose Third Army received priority allocation of proximity-fused ammunition, documented the devastation. On the night of December 25th, his artillery caught a German battalion attempting to cross the Sauer River near Echenach. A single battalion firing proximity-fused shells killed 702 German soldiers by actual count. Patton wrote to the War Department, "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration, and killed by actual count 7,002. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." Between December 1944 and March 1945, from the Battle of the Bulge to the crossing of the Rhine, proximity-fused anti-aircraft shells firing against German aircraft brought down over 1,000 enemy planes. In ground combat, proximity-fused artillery shells calibrated for airburst detonation took fearful tolls. Advanced fire control radar enabled artillerymen to destroy targets on reverse slopes of hills and beneath forest canopy, where conventional fire was impossible. The Germans captured approximately 20,000 proximity fuses when they overran an American ammunition dump during the Battle of the Bulge. German ordnance experts examined the fuses, but concluded they could not possibly function as intended. The technical specifications seemed impossible. Electronics that could survive artillery launch forces were considered beyond current technology. The Germans assumed the fuses were some kind of advanced time mechanism they did not fully understand. The fuses were warehoused and eventually abandoned as German forces retreated. The secret remained secure not through security measures but through German disbelief that the technology could exist. March 1945, Iwima Bonin Islands. American forces preparing to assault the heavily defended island faced concentrated anti-aircraft and shore battery positions. VT proximity fuses were modified for use in bombs dropped from aircraft. The fuses detonated several feet above ground, creating airbursts over enemy positions. B-24 Liberator bombers dropped proximity-fused bombs on Japanese anti-aircraft positions before Marines landed. The results exceeded expectations. Airburst detonations caught Japanese gunners in the open and destroyed equipment that would have remained undamaged by near-miss ground bursts. By August 1945, over 22 million proximity fuses had been manufactured at a cost exceeding $1 billion in 1940s currency. Each fuse contained 130 miniaturized electronic components. The supply chain involved 87 firms using 110 factories. Crossley Corporation, RCA, Eastman Kodak, General Electric, and McQuay Norris served as primary assembly contractors with over 2,000 suppliers providing components. At peak production, the American electronics industry manufactured 70,000 fuses daily. The cost per fuse dropped from $732s in 1942 to $8 by 1945 as production techniques improved and economies of scale took effect. Secretary of the Navy James Forrestal stated after the war that the proximity fuse helped blaze the trail to Japan, noting that without the protection this device provided to surface ships, the westward advance could not have been so swift, and the cost in men and ships would have been immeasurably greater. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitchell, commanding fast carrier task forces, recalled that all 5 ammunition in 1945 was fitted with proximity fuses, and those fuses knocked down enemy planes by the dozens, preventing ship losses and casualties that would have been enormously larger without this technology. British Prime Minister Winston Churchill noted that proximity fuses made in the United States proved potent against the V-1 rockets that assailed Britain in 1944. The Japanese never fully understood why American anti-aircraft effectiveness had increased so dramatically after early 1943. Post-war interrogations of Japanese military officials revealed that most believed Americans had developed superior fire control radar or had integrated aircraft detection with gun directors in ways Japan could not match. Some Japanese engineers speculated about radio-controlled shells but dismissed the concept as technically impossible, given the forces involved in gun launch. The idea that individual shells could carry miniaturized radar systems seemed beyond credible technology. This failure of imagination allowed the proximity fuse to remain operationally secret throughout the war. The human cost of Japanese failure to develop equivalent technology is substantial. Japanese naval aviation lost over 12,000 aircraft in combat during the war. Documented evidence shows proximity fuses accounted for destroying several hundred of these aircraft directly through anti-aircraft fire. Each aircraft represented not just material loss, but trained aircrew impossible to replace. The death of experienced pilots in 1943 and 1944 Japan to commit poorly trained replacements who fell victim to American defenses at unsustainable rates. By 1945, Japan resorted to kamikaze tactics, partly because conventional attack methods had proven ineffective against American ships equipped with proximity-fused ammunition. The broader impact of proximity fuse technology extended beyond World War II into modern military development. The techniques developed for miniaturizing electronics and hardening components to survive high acceleration became foundational for subsequent advances. Missile guidance systems, space exploration, and modern artillery all benefited from innovations pioneered by the proximity fuse program. The concept of distributed intelligence, where individual munitions carry sophisticated sensors and processors, traces directly to VT fuses. Modern smart munitions that can sense targets, discriminate between targets, and optimize detonation represent evolution of principles established between 1940 and 1945. Dr. Merle Tuve, returning to the Carnegie Institution after the war, rarely spoke publicly about his role developing proximity fuses. When details were finally released, Tuve deflected personal credit, emphasizing the contributions of hundreds of engineers and thousands of production workers who transformed theoretical concepts into millions of reliable fuses. His modesty understated his essential leadership in a program that War Department officials ranked second only to the atomic bomb in strategic importance. Without his insight that radio proximity detection could be miniaturized sufficiently for artillery shells, without his persistence through early failures when success seemed impossible, the proximity fuse would have remained a theoretical concept rather than combat reality. The production achievement equaled the technical accomplishment. Manufacturing 22 million proximity fuses, each containing 130 precision components, required industrial organization on unprecedented scale. Over 100 factories had to coordinate delivery of components matching specifications measured in thousandth of an inch. Supply chains had to deliver vacuum tubes, batteries, and electronic components from hundreds of specialized suppliers, all synchronized to keep assembly lines operating at capacity. At 70,000 fuses per day, production required approximately 9 billion total electronic components over the course of the war. The proximity fuse stands alongside radar and penicillin as one of a handful of technologies that materially affected World War II's outcome. Unlike radar, whose development occurred in multiple countries, the proximity fuse resulted from deliberate application of existing knowledge to a specific problem. Dr. Tuvit and his team at Section T identified what needed to be done, determined how to accomplish it, and executed a program that achieved operational capability in under 3 years. This focused approach to weapons development became the model for Cold War military research. The Manhattan Project developing atomic weapons followed similar organizational patterns. Post-war missile programs adopted the same structure of university laboratories, industrial contractors, and military oversight. The legacy of those 20,000 G-rated fuses extends beyond their combat effectiveness into how nations organize scientific talent for military objectives, how industries manufacture precision electronics at scale, and how seemingly impossible technical challenges yield to sustained effort, backed by adequate resources. The miniaturized vacuum tubes that seemed impossible in 1940 became routine by 1945. The precision manufacturing that required specialized technicians became automated as production techniques advanced. But in 1943, 1944, and 1945, as Japanese aircraft fell from the sky, as German infantry died under precisely timed airbursts, as V-1 missiles disintegrated over the English Channel, the proximity fuse represented the cutting edge of what human ingenuity could achieve. Lieutenant Red Cochran, watching that first Japanese Naval disintegrate on January 5, 1943, understood that something fundamental had changed in aerial combat. His gun crew had destroyed an aircraft without perfect aim, without precise fuse setting, without any of the calculations that had limited anti-aircraft effectiveness for decades. The shell had done the work, sensing the target, timing its own detonation, achieving what human gunners could only approximate. In that moment off Guadalcanal, a new era in warfare had begun. The age when individual munitions carried intelligence sufficient for autonomous operation had arrived. The story of the proximity fuse proves that sometimes the greatest victories are won not through destruction, but through demonstration, not through propaganda, but through prosperity of ideas, not through hatred, but through the application of scientific method to the brutal realities of modern warfare. The German soldiers and Japanese airmen who faced proximity fuses never understood what killed them. They reported only that American defenses had become impossibly accurate, that ships seemed able to shoot down aircraft regardless of maneuvering, that artillery created explosions that seemed to seek targets with supernatural precision. The proximity fuse did not win the war alone. No single technology did, but it contributed to victory in ways that saved thousands of American lives and accelerated Axis defeat by making aerial offensive operations unsustainable against well-defended targets. Those 20,000 graded fuses, each one representing the technological limits of 1940s science, turned American artillery into a weapon system that enemy forces never expected and could never effectively counter. They remain a testament to what free societies can achieve when scientific curiosity, industrial capacity, and strategic necessity align in pursuit of a common goal worthy of such extraordinary effort and innovation.